I want to talk today about a purification technique called recrystallization. It's used when we have a solid product that's contaminated with some sort of other solid that we want to remove from it. It depends on differences in solubility between the product and the contaminant. Sometimes we use a single solvent in recrystallization, but other times we can use 2 or even more solvents to generate a solvent mixture that has the appropriate solubility profile for our product and our contaminant. There are 2 different basic scenarios that we're going to look at. One is when our impurity is insoluble, and the other is when it's soluble. And the first one I want to look at is removing the impurity or the contaminant when it's an insoluble impurity. In this particular case, we have a solubility profile that looks like this. And what I've graphed here is the solubility versus temperature of a product and an impurity. And what you can see is the product has very low solubility at low temperature, but as we heat it up, the solubility increases substantially. Whereas for the impurity, the solubility stays the same and fairly low no matter how high we put the temperature. So if we look at how this solubility profile is going to allow us to purify our desired product, we start off with our solution that has our product, which are these darker black specks, contaminated with some impurity, which are the red specks. And we take our sample that we're purifying and we heat it on a hot plate. And because of the solubility profile, what's going to happen is that as it gets warmer, our product that we want is going to dissolve because its solubility goes up. But the impurity, since its solubility doesn't increase as the temperature increases, it stays undissolved. So since our product's solubility has increased, you can see that it's dissolved. The impurities are still there on the hot plate. So now we've physically separated the 2. Now we just have to isolate our product from our contaminant or our impurity. And the way we do that is to filter off the solid impurity. So now our solution contains only the product. And it's a clear solution because it contains only the product and the product soluble. So we're up here on our solubility curve right now. How do we get our solid product back? We cool it back down and its solubility decreases and the product comes out of solution. And you can see we have our solid product without the contaminant or impurity in it. And we'd probably isolate this solid by filtration. The next case I want to look at is removal of a soluble impurity by recrystallization. In this case, the solubility profile that we're looking at looks something like this, where the product behaves similar as before, insoluble at low temperature, much more soluble at high temperature, but the impurity is soluble at all temperatures. In this case, we take our solid product with our solid impurity, and we add solvent to the mixture. And it's going to be not a lot of solvent. It's going to be the minimum amount of hot solvent. We want to do this in warm, hot. And you generally want this solvent to be close to its boiling point. You're not going to add it all at once. You're going to add it in small portions until you get to the minimum amount of hot solvent to dissolve all of our material. And since both the impurity and the product are soluble at high temperature, you can have a clear solution. Everything's dissolved. Now, in order to get our product, what we do is we cool the solution. Since now we're not at high temperature, we're at low temperature, our product is not very soluble. It reforms a solid, recrystallizes, comes out of solution, whereas the impurity, which is still soluble at low temperature, stays dissolved. We've now separated the impurity from the product, and we isolate our product at this point usually by filtration. And after we filter it, we can isolate our product, and we've purified our product. One last thing I want to point out to you about this recrystallization process is it really depends on differences in solubility between the product and the impurity. So in a case where the solubility profile looks like this, where the product and the impurity have similar solubility profiles in your solvent, you can't use this solvent for recrystallization. You either need to find a different solvent or use a different purification method. If we shift gears a little bit and talk about the recrystallizations that we're going to be doing in our lab, starting with the benzoic acid, you take your impure benzoic acid, you put it in a beaker, and you add the solvent that you decided from your previous work would be the best recrystallization solvent for benzoic acid. You then heat this on a hot plate with a boiling stick. The purpose of the boiling stick is to stop the solvent from bumping as you heat it near its boiling point. Sometimes you might use a stir bar for this, not so much in a recrystallization. Sometimes you would stir it manually to prevent the bumping, but we need to stop it from bumping, and that's what the boiling stick does. You'll notice with just 10 mils of solvent, it hasn't dissolved yet, so we're going to have to add more hot solvent until it just dissolves. We don't want to add too much because then we'll lose some product. And this is a case where our product and our impurity is soluble, so after we've added the appropriate amount of solvent, we have a clear solution where both have dissolved. Now we want to cool the solution. When we cool the solution, our desired solid will come back out of solution, the impurity will stay dissolved, we filter the product, then we dry it, and we get a weight on the product after it's dry. In the second recrystallization we're doing with dibromobenzene, we're going to add dibromobenzene to our ethanol, and we're going to heat it to dissolve the dibromobenzene and the impurity that's mixed in with our dibromobenzene. Now in this case, what we're going to do is we're going to add something called decolorizing carbon, which is a solid carbon which will absorb our impurities. So after we've added, we want to make sure we cool it briefly before we add it actually. And then we add the decolorizing carbon. We have a solution that has our dissolved dibromobenzene and the decolorizing carbon, which has absorbed our impurity. But now the decolorizing carbon becomes an insoluble contaminant in our solution that we need to get rid of. And we do that, as we said before, by filtering the solution. So we're going to filter off the decolorizing carbon while we're on the hot plate to make sure that the solution keeps dissolving our product and to make sure that we're ready for the next step where we start adjusting the solubility of our product as well. So once we've done that filtration, so we have our clear solution because we filtered off the solid decolorizing carbon, we start adding water to the solution dropwise. Water will make our compound less soluble in the solution. So we want to add the minimum amount of water to get it to come back out of solution. Once we do this, we add a few drops of ethanol back to the solution so that it clears up again, and then we cool it to get our product out. We cool it on an ice bath, we filter, and we dry and weigh our product.